Alrighty, so today we have Twitch issues, which is why we're doing it this way. Upload speed is still terrible. So this is Proton NMR Spectroscopy, or 1H, as you'll see it written. So this is going to be our more useful method of determining the structure of organic molecules. And how this works is through the phenomenon of nuclear magnetic resonance. And this kind of first bit of the lecture today, I'm not going to be asking you things about. The theory of NMR is complex. It's physics. I'm not going to be overly concerned with it. So we're going to just have a brief little intro here. And we're going to see later on what all this will tell us. So suffice it to say that nuclei with odd mass numbers, like 1 for a proton, hydrogen, as we know, most hydrogen has a mass number of 1, no neutrons. When these are rotating, we're going to see that because they're charged, as a nucleus rotates, as a charged species, it generates a magnetic field. This is physics, right? As you rotate something that is charged, you generate a magnetic field. And suffice it to say, the direction that the kind of nucleus is spinning, as it were, as it's rotating, kind of determines the direction of that magnetic field. If it's spinning one direction, that might end up having the magnetic field with the north on top, south on the bottom. And if it's rotating the opposite direction, you'll have the opposite for your magnetic waves. And so we might kind of draw this as this kind of a bunch of nuclei just kind of having magnetic fields in all these random directions. They're small magnetic fields, so this is kind of normal. But if we apply a magnetic field, we're going to see that some of these will align with it. And some will be against it. So some will line up with the magnetic field, which is indicated by the letter B, as physics would have us do. Again, this part, don't worry about. Suffice it to say, some will end up aligning with your magnetic field, some will oppose it. It just happens to be whichever way they'll be looking. And as a result, we end up with an energy difference between those two. We have an energy difference for those that are aligned, that have lower energy. And we'll have some that oppose it, and those are going to have higher energy, right? So that's always kind of just how all this works, right? You have something aligning with it, and that's going to be a good, nice interaction. And if it opposes it, we have the opposite problem there. So with this, we're looking at essentially what happens when they're aligning or opposing. And it turns out that as things are aligned or opposed, some of the opposed ones, or rather some aligned ones, will absorb energy and they'll flip. And so let's say this one and this one decide to flip. They go to a higher energy. They're absorbing energy, right? So they go up to a higher energy state. And as they do that, we can detect it. We can detect when protons, or rather any nucleus, is absorbing energy and flipping its orientation. And that can be detected. And so we can tell what... as a result, we can tell how much energy because this is quantized, just like absorbing light energy to excite an electron to a higher state. We saw that there were specific energy levels that we would detect. And so with this, we can do the same thing. We can see how much energy they're absorbing and how frequently. Just like kind of how many there are. Well, let's erase that. So how many nuclei absorb it? And this is going to tell us everything that we need to know about a molecule, believe it or not. Because we're going to see that depending on the nucleus, what's kind of hanging around it, things are going to behave differently. And so this tells us essentially kind of the type of nucleus and what's nearby it. And we're going to see that this will tell us kind of how many there are. I just wrote exactly what I wrote for number 2. So we'll see what this means. We're going to see a nucleus magnetic field is affected by nearby electrons. And we're going to see that if you have a lot of electrons nearby, that's called a shielded nucleus. Because you have all these other electrons, which are also charged particles, and they are rotating about and moving, thereby generating their own magnetic fields. And so the more electrons you have nearby, you have competing magnetic fields that are going to shield your nucleus from the applied magnetic field. If you only have a few nearby, you are called a de-shielded nucleus. So you are now more exposed to it, and so you're more likely to absorb the energy. And so just by looking at how much energy is absorbed at what level, that tells us about the nearby electronic environment for your nucleus in question. And so we're going to see here that all of these factors are going to come into play. I'm not terribly concerned if you know this theory. I'm more concerned with the practical aspects of this, because you can go ahead and watch a YouTube video on how NMR works, and you can see the machines and all that. But suffice it to say, you're just looking at when nuclei are absorbing magnetic field energy and flipping their spin. And that's it. That's all it is. Seems very simple, right? And it turns out that this depends also somewhat on the field strength that you're using. So a lot of this, the change in energy between aligned and unaligned, rather opposed, depends on your magnetic fields, right? Remember, B is magnetic field. So we see that if you have a small magnetic field, you have a particular delta E between your aligned and your opposed, right? And if you have a bigger B, a bigger magnetic field, you have a larger energy difference. And it's proportional. So this all just is proportional to your magnetic fields. We're going to see that having a larger energy gap means it's easier to resolve your signals. And the reason for that is because if they're smaller, very similar nuclei will kind of overlap together. And the farther apart you make them, it makes it easier to detect when one is... Here, I'll do something like that for a slightly different nucleus. So with a slightly different environment. Hopefully we can see here that the difference between these two is pretty small, but it's a little bit bigger here. Because proportionally they're both expanding, right, as you have the larger field. But we can see here that it may overlap because they're so close together in energy. But now that we have this a higher magnetic field, we see a bigger difference in energy between the two different types of hydrogens. And as a result, you get better resolution with that. And so, suffice it to say, the stronger magnet is better resolution. And of course, to have a stronger magnet, that means stronger wallet, right? So we're going to see here that for Proton NMR, you can get away with using a fairly cheap, and by fairly cheap, I mean tens of thousands of dollars, because hydrogen is so abundant and all that. And that's typically around, we're looking at around 60 megahertz for your magnetic field for this. It's about like 1.5 Teslas is the magnetic field strength. This is about $80,000 or so. Very basic. You can really only ever look at hydrogen using this. You get up to 500 megahertz, really good resolution. These are millions of dollars. I've seen I think a 900. This is, tens of millions of dollars. As you get to stronger and stronger magnets, you get better and better resolution. You really need this super better resolution for looking at very complex samples like proteins. But for relatively simple molecules, if you're just looking at hydrogen, 60 will do you just fine. Not very good, but the more you see that you can just keep acquiring more and more spectra, and the more you do, you can add them all together and get that. So suffice it to say, these are tens of millions of dollars. These are not instruments that we have handily at the college. We would have to go over to the base to look at their machines and all that. I'm not really worried about the machines, though. You can read about them. You can look at them. In terms of your sample, though, thankfully, if we're doing Proton NMR, anything with protons, with hydrogens, will suffice. So you can use anything that has a hydrogen and take an NMR spectra of it. So it's great. However, typically it's done in solution. Very often we don't have solid samples that we do NMR with. We need them in solution so they're able to rotate. And what this means is that we need to use a solvent, right? But the problem is, solvents have hydrogens too. Solvents have hydrogen. And so, as a result, because your solvent is so much more than your solute, all you're going to see is the solvent. So the workaround here is we use deuterated solvents. For example, this is chloroform. Chloroform D, they would say. Deuterated chloroform has no protons. It makes a good solvent. It dissolves most things. It's slightly polar, so it'll dissolve your non-polar things. It'll dissolve some of your polar things. You can have acetone D6. A little bit more expensive. CD2Cl2, methylene chloride. These would be fairly common solvents. D2O, deuterium oxide, or heavy water would be another example. You just want to make sure your solvent does not have hydrogen in it. So it would need to have deuteriums instead. Deuteriums, remember, have even numbers of even mass numbers, so they're not detected by NMR, at least in the frequency we use. So these would all be invisible to NMR. And that's what we want. We don't want to see our solvent, we want to see our sample. So anything with hydrogen will be detected by NMR, by Proton NMR at least. But if we use these deuterated solvents, those will be invisible. So we can go ahead and use our things. So let's take a look at what a spectrum looks like. And we're going to see that we're going to be able to tell a lot of information. So at this point now, this is the stuff I want you to know. So let's look at a spectrum. So in NMR Spectrum, I'm going to try and make this, okay, I have to like drag it over here. So here is an example of an NMR spectrum. This one is, it's ethylbenzene. They apparently use a 90 megahertz magnet on it, and they gave some solution information. So notice their solvent is deuterated chloroform. So no protons there. So all we see is information about ethylbenzene. And so, what the heck does all this mean? What is all this stuff? The spectrum itself, we're going to see that we're going to get 3 bits of information out of there. And they're all going to correspond to useful bits about the sample. So, I'm going to move this over. I will try and just copy that real quick. We had, let's see, and then we had the triplet. And this is just about 7. Okay. So there's 3 bits of information here that we can get from a spectrum. First thing is how many signals? And that really is how many groups of peaks. And here we've got 3 different peaks, or groups of peaks, right? We're going to see that tells us how many signals we have. And we're going to see the corresponding information to this is how many, what would be the ways to this? Non-equivalent hydrogens there are. And we'll see what we mean by non-equivalent in a second. So the number of peaks on your spectrum tells you how many types of hydrogen you have. And by types, we mean their like kind of immediate environment. So it's going to tell us stuff about the symmetry of the molecule. We can also tell where these peaks are. This is what's called the chemical shift. This is your x-axis. What this tells us is what is nearby. What is the environment that hydrogen is in? What sort of electronic influences is it experiencing? What do I want to say next? How about what shape are the peaks? This is called multiplicity. And this information also tells us how many nearby H's we have. And then the last thing is how big are these peaks? And really, we actually integrate them. And that means we're not doing math. We're not doing the math here. But remember that an integral gives you the area under the peak, right? Under a curve. And so that tells us how many hydrogens of each type we have. So that's directly correlated with number one. Number one tells us how many types, I'm going to just say types of this then. How many types of hydrogen you have. And the last bit here, how big the peaks are, tell you how many of hydrogens of each type. In this case, we had 3 different types of hydrogen. If we were to integrate these, well, we'll do that in a sec. All right, so 4 bits of information. I'm going to make this vertical for a second here. We get 4 bits of information out here. And believe it or not, all of this information is all you need to figure out the structure of a compound. It's a lot of work because you're going to have all these bits of pieces of information that you're going to need to put together to figure out your compound, what its structure is. And so we're going to kind of look through these one at a time, and we're going to get some information about each. All right? So this is ethylbenzene, by the way. The structure that we kind of showed. So it's just ethylbenzene. That molecule gives this particular spectrum. And don't worry, I'm not going to be hand drawing anything for you on your exams. I'll be using actual spectra, or rather predicted spectra. So we'll see. Alrighty, so let's take a look at the first one here. We'll look at how many signals we see, and we'll learn how to identify types of hydrogens. So, So we're going to look at this one first. How many peaks do we see? Well, this all comes down to symmetry. So what this question answers is the question of which hydrogens are equivalent to each other in a molecule. And this really deals with symmetry. So if we take a look at something like butane, we're going to see that because of symmetry, we really only have two types of hydrogens on this. This is just bugging me. Oh, okay, I'm going to fix it. Hydrogens. There we go. We're going to see that butane only has two different types of hydrogens. Suffice it to say, I'll go ahead and draw them. If we were to consider the environment of these, we would see that the green hydrogens all experience relatively the same thing as each other. They are all part of a methyl group, and they're all just nearby other carbons. And they're kind of at the end of the molecule, right? We're going to see that the blue ones will also experience similar kind of environment as each other. And so we're going to see that butane has just two types of hydrogens. So we would see two types. We should therefore see two peaks only. And indeed we will. But let's take a look at how to figure out if they're equivalent or not. First way is through symmetry. If there's any symmetry whatsoever, they will be equivalent. This can be in terms of an axis of symmetry or a plane of symmetry. Any sort of symmetry whatsoever, they're going to be equivalent to each other. And so if we take this molecule and rotate it about, I'm going to go ahead and rotate this molecule. I'm going to stick an axis right here, and I'm going to rotate this molecule 180 degrees. And if I do that, this is what I get. It's the same thing. So, any hydrogens that experience an axis of symmetry that's symmetrically identical, they are going to be equivalent to each other. And we're going to see that we can do it with a plane of symmetry too. If I mean, it'd be the plane of this chalkboard here, right? Or this screen. But it would be essentially the same thing. So with this, anytime you have symmetry in your molecule, those hydrogens would be equivalent to each other. Maybe more prevalent here in this example. But we're going to see that this molecule has a plane of symmetry. It doesn't have an axis of symmetry, because we can't just rotate this around whatever angle we want and get the same thing. This is a methyl group, by the way. If we do that, we do have a plane of symmetry, though. And actually, I'm going to make it a chlorine. Why not? It'll be a little bit easier. We do have a plane of symmetry here, which tells us that everything on the other side of the plane is symmetrical. And as a result, it would be chemically equivalent. And so, remember, chemically equivalent means they're going to show up in the same place on NMR. So, if we're looking at it, we would say that these two hydrogen A's would be equivalent to each other. The hydrogen B's would also be equivalent to each other, because they are identical through symmetry. And then hydrogen C is by itself. They're all alone at the bottom. We would see overall 3 signals. And thankfully with these, when we're thinking of symmetry, we can even think about localized symmetry. And so, if we think about it this way, I'm going to put all our H's out. And I'm going to just go crazy and make sure that we have no hydrogens on this whatsoever. One more. Okay, so no hydrogens up here. We are still only going to see 3 things. We're only going to have 3 signals here as well. Unless we're using some super complex one that's going to see things from far away, but we're pretty much going to see 3 things here. Because this hydrogen, if you want to think about it this way, there is still localized symmetry here, right? We still have those 2 on either side of the molecule. Because that thing is rotating up there, right? That fluorinated thing, whatever butyl group, sect butyl, is rotating about. Overall, these 2 hydrogens, those are carbons, but the hydrogens on them would still be equivalent to each other. That top group is just rotating around, and overall the symmetry still has it the same way. If you want to think about it, look at what's around your hydrogen. If we're looking at HA, this HA feels the effects of basically things 1 carbon away. So it feels the carbon to the sec butyl with all the fluorines. And it also feels the carbon to hydrogen B. I'm going to write this down here instead. If we think about this one feels the carbon next to the sec butyl with all the fluorines. And it also feels a carbon to a hydrogen, right? I'm going to get rid of those. So in fact, these 2 are feeling the same thing as each other in terms of electronics. So their environments are the same. And so as a result, these are equivalent to each other. And the same thing for B and C, right? So we'll see what that looks like. All right, so when we're looking at these, it's all a matter of determining symmetry, if there is some, or you can think about what they see or feel. And if they're feeling the same thing as each other, then they will line up in the same place. They will be chemically equivalent to each other in terms of NMR. Couple of important bits here. That all H's on a methyl group are equivalent. So all the hydrogens on a single carbon are usually equivalent to each other. We're going to see that all H on a CH2 are also equivalent to each other, but we've got some ifs here. if it's sp3 and not chiral. And by that I mean these three H's are equivalent to each other because they're on a methyl group. So they are equivalent to each other. Are they equivalent to anything else? Not in this case. These two hydrogens are equivalent to each other because they are sp3, and the molecule is not chiral. Don't worry, I'm not going to be giving you chiral molecules for NMR. So don't worry about it. So on an sp3 carbon, the two hydrogens there will be equivalent to each other. And now we have this other set of hydrogens over here. Those would all be equivalent to each other because it's an SCH3. But are these two the same? And no, they're not. They don't see the same things. HC, they are on a carbon right next to a carbonyl. HA is not on a carbon right next to a carbonyl. So they don't feel the same. They are not the same as each other. And of course, HC and HB can never be the same because you have 2 protons versus 3 protons. Those will never be identical to each other. So whenever you're comparing if things are identical, you have to consider how many and where they are. And so for this molecule, we would see 3 signals. We would see, aha, we've got HA, HB, HC. Those are the 3 different types of protons we have on this molecule. This one, however, only will have 2 types. If we draw them all out, got HBs here. And what other color do we have? Orange. We will see here that because of the symmetry of this molecule, HB and HC are the same as each other. They see the same environment. They are on a CH2 that is adjacent to a carbonyl and adjacent to a methyl group. They feel the same things. In terms of HA and HD, those are also going to feel the same things. So HA and HD are the same as each other due to symmetry. All right, this molecule has a plane of symmetry right through the middle, right? We have a plane of symmetry. The more symmetry we have, the fewer signals we're going to see. So even though there are many hydrogens here, we only see 2 types. We see the hydrogens on the CH2 and the hydrogens on the CH3. Right, on the other side of the molecule, they're all identical to each other. On something like this, cyclohexane, we would only see 1 signal. Because all these hydrogens are all equivalent to each other. They all see the same thing. They all just see all the same things. So all of these all of these see the same things as each other. They see a CH2 right next to them, and that's it. That's all they see on either side. And so all of these will be the same. Now, interestingly enough, the reason that we know these chairs exist, by the way, the reason for all these chair things, we would actually see a difference between axial and equatorial hydrogens if we like really cooled this down. But that's this kind of outside the scope of this. Normally, we would see one signal because they're all the same. But we know that some of these are going to be axial, some are equatorial because it's cyclohexane. And if you really cool the temperature down where it can't flip anymore, where you're stuck with one, ones that means you have 6 hydrogens that are for sure axial and 6 are equatorial and nothing changes, they don't flip, then you'll see 2 peaks. But that's really, really cold temperatures that you'll see that, so don't worry about that. So there are some temperature effects, but don't worry. Chairs are flipping back and forth all the time. There's no reason that it would flip one way or another, so you're only going to see one signal here. All right, if you threw out something like a T-butyl group or something, yeah, you're going to see more signals. So we'll worry about that later. Benzene, of course, you'll only see one. Here, let's go ahead and look at the... if you had T-butyl cyclohexane, if we draw in all the hydrogens, maybe down one, maybe up. We're going to see that we're going to get a crap ton of signals. We'll have this one. Of course, we'll have all these. And these will all be equivalent to each other. We're going to see that this would be different than that because the hydrogen C is equatorial. Remember, this thing is not going to flip. T-butyl group is never going to be axial. So because it's not going to flip, you'll be left with more specific ones. You'll probably see these, at least 6, and the rest would probably all glob together. Or you may see something like these axial ones all being the same, and these equatorial ones all being the same. Just farther out from the T-butyl, they don't see the T-butyl, so they just see other hydrogens. So they would probably be equivalent to each other, but yeah, that's what we're looking at here. So we would see a lot of signals. Because of that. And we may think, oh, well, we have different ones, but because we have axial and equatorial ones that aren't flipping, those are going to behave differently. So I and G, for example, don't see the same thing as each other. They are separate. All right, let's take a look at some more like normal molecules and see what we can do here. Let's see how many signals we would expect from all of these. And so, while this is chiral, I'm just going to pretend it's not. The one on the right. The one on the left isn't. But good thing to do would be to draw in all the hydrogens, right? So if we do this, we're going to see that we're going to have probably 4 types of different hydrogens on this left molecule. We'll see that these will all be the same as each other, of course. These will be the same as each other. This one's going to be its own thing. But what about these other ones? Are these going to be the same as each other? Are D and E going to be the same? Yes, they will, because they all see the same thing. Right? They see a carbon to a hydrogen C. That is what they see nearby them. So because D and E see the same thing, those are going to be the same. Do they see the same thing as HA? No, they don't. Even though these are all CH3s, HA is next to a CH2. HD and HE are next to a CH. So they see different things. And so as a result, we're going to see 4 different signals. We'll see 1 signal, second signal, third signal, fourth signal. Because HD and E are the same, we're going to see 4 different signals here. All right. Let's look at this one. Let's draw in our hydrogens. I'm just going to label them. We know all the HAs are equivalent to each other. In this case, we don't even have a question about it. We have no question because none of these could be identical to each other because they have different numbers, so 3 signals. So even though this is chiral, we're assuming it's a racemic mixture, we're going to see 3 signals. I'm going to avoid chiral molecules. So technically, we may see certain things happening with HB and HC that are a little weird, but don't worry about it. For right now, don't think about chirality. Just think what's on it, what's nearby it. Do they see the same things? HCs see a bromine, they see a carbon with a chlorine. Obviously different from HA, which sees just the carbonyl, and so we're going to see 3 signals there. All right, let's see, what else do we want to do? Good stuff. So, let's do just a couple more. This one I gave on an exam once. Believe it or not, this thing you only see 3 signals. No matter, I mean, look at how many hydrogens there are. This was a fun one on their exam. They either got it right away or they didn't get it at all. I'm drawing them in different colors so you can see these are the different types. All through symmetry. So even though this molecule is C15H 6 times 3, 18, 19, 20, 21, 22, 23, 24. Like, wow. You'd say, oh, well, look, there should be 24 different hydrogens here, but you only see 3 signals. 3 peaks. Because they're all equivalent to each other. Or most, I mean, all the green ones are equivalent, all the blue ones are equivalent, all the purple ones are equivalent to each other. So they all see the same thing due to that symmetry. So CH3s, they all see the same. They all see the same as each other, even though they're far apart. all because of symmetry. So generally with H24, you'd be expecting a lot of signals, but not the case. So that would be a good thing to do. All right, so those are kind of our rules of determining things if they're equivalent or not. What we haven't talked about is things with double bonds. With something like this, we're going to see one, two, three, four, five types, actually. We're going to see 5 signals here. Because HA and HB are not equivalent to each other. The reason for that is because on a double bond, they can't rotate. On single bonds, they could rotate. Normally, CH2s would have equivalent protons to each other, right? We saw like HB and HC in this molecule right here. Though HB was equivalent to the other HB because it could rotate. There's symmetry and all that sort of thing. With this, these can't rotate, so AC is more of that isopropyl group, BC is more of that methyl group. And as a result, they're different from each other. So on a double bond, CH2s may not be equivalent to each other. They could, they might, if we had the same thing, if we had isopropyl on both sides, then we would see the same thing, because then we'd have symmetry. If we had this, we would only see 3 signals. That's it. 3 signals here. And here we would see 5. So HA and B are different because they see different things. Because they're locked in place, HA sees that isopropyl. It doesn't really see the methyl. Or rather, better to say, it sees the isopropyl as a cis relationship to itself and the methyl as a trans relationship. HB would see the isopropyl as trans and the methyl as cis to itself. And so they see things differently. And so they are going to not be equivalent to each other. So you're going to see 5 different types there. You've got the purples, the blues, the green, and then A and B. All right, so with double bonds, things can get a little more messy. So it just depends on your symmetry. All right, and so we are going to learn ways, by the way, to detect these. For example, that molecule versus this one. Versus this one. We are going to be able to tell using NMR. These all have 3 signals. So we're still going to see 3 signals for all of these. All of these molecules will have 3 signals. We're going to use other information though to tell them apart. So, hopefully, we're getting a hold on this. We have different types of symmetry in all these molecules, but we still have 3 because of all that symmetry. With something like this, we have no symmetry, so we are going to see all of them distinctly, except for the isopropyl that has some local symmetry. An isopropyl group, by the way, will always just have 2 signals, so something to keep in mind. And so we're going to see patterns there. All right. So let's talk now about our next category, the chemical shift. All right. So a good idea to figure out how many signals you have. Just take a bunch of carbon molecules, take a look at them, maybe take all the ones in that IR exercise and determine how many different types you'll have. All right, so what's equivalent to each other? All right, so that was the number of signals. Next, we're going to look at where those peaks are on the spectrum, which is called the chemical shift. All right, and so let's take a look at what that will mean. So if you need a break, this is a good time to do it. Take a break, pause the video. Chemical shift. We're going to see that de-shielded versus shielded nuclei will interact with things differently. And so the first thing that we want to do is standardize this. So we say we have this compound tetramethylsilane, TMS. We set this one to be 0. We say that this is kind of the least de-shielded you can be. So we say that these are going to be our most shielded nuclei. So there's nothing in here that's going to be taking their electron density away or anything like that. These are going to be the most like normal nuclei that we have. And so we set this to 0 ppm, parts per million. We're going to see where that unit comes from. So we set this as our 0. And we're going to say that anything more de-shielded will have a larger chemical shift. Again, this is parts per million. We usually use the letter delta for chemical shift. By the way, so you'll see that a lot, and it'll tell us things. Now, what's important to know is that the strength of your magnet does not affect the chemical shift, because these are all relative to each other. So it's all basically your 0 ppm is your tetramethylsilane. Typically, your deuterated solvents have been spiked with just a little bit of TMS, so that you will have a peak at 0, so you can reference that and set your peak to 0. Although typically we don't show that. And really we're just comparing how de-shielded is this nucleus compared to TMS's nuclei. TMS, by the way, there's 4, all those are equivalent to each other. And so you only see one signal for TMS. And so whether that's shown or not, in this example that I showed you about the ethylbenzene, we do not see a TMS peak, but we would see a singlet there. One single peak, and that's where it would be at 0. Everything else is more de-shielded. And so we describe, here's our axis. This is where TMS will show up. It would show up as a single peak at 0. And so, we go up here, 5 to 10. Usually we go to about 12 or so. 12 is about the maximum that we see, normally speaking, at least for Proton NMR. So usually we're going between 0 to 12 ppm. The parts per million, by the way, comes from the Hertz values that are associated with these. It's a unitless quantity, but I'll give you an example in just a second. Relatively speaking, we kind of call the right side of the spectrum the upfield region, and the left side more downfield. These are terms we say relative to each other. We would say that middle peak right here is downfield of this peak, the peak at about 1.2 or so. So upfield and downfield are relative positions. This peak is the most downfield. This peak is the most upfield. It is upfield of this peak and downfield of this peak. So these words, by the way, come from like how NMR used to be done. It used to be done kind of manually, where you'd screen like these different frequencies, one by one, which was terribly tedious. Now it's all done at once. You scan all the frequencies at once, and you do a Fourier transform and do all this lovely math, and poof, you get your spectrum. But these terms still show up. So that's why we still have these terms. So relatively speaking, good reference peak is chloroform. The proton here shows up at about 7.26 ppm. Or the book has it at 7.27, whatever, that's okay. Typically, though, this is calculated by the shift from TMS over your kind of magnetic field. And depending on what your magnetic field is, your shift from TMS will be slightly different. So the more d-shielded you are, the fewer electrons you have blocking your nucleus, so you're more likely to get flipped over, right? So let me just say that again. Fewer electrons nearby, d-shielded, more likely to flip, right? To resonate. That means you're flipping from being aligned to being opposed to your magnetic field. So the more de-shielded you are, the bigger your shift from TMS is. So we say that TMS is our 0 point. So in a particular field, we'll see that the chloroform proton will flip 436 times more frequently than the TMS one does. And we'll say this is our 60 megahertz instrument. You do that, you get unitless quantity. But that's the value you get. If you're doing this in a better instrument, you'll have more, right? The more frequency you have, the more you're going to affect this. Apparently for this, you'd get that. And notice you get the same value. Well, and so we see that Hertz cancels out, right? But instead of writing all these 10 to the negative 6s, we just say ppm instead. And so for chloroform, we're going to say that this proton shows up at 7.27 ppm. I learned it as 7.26, so that's why it's still stuck in my head that way, but close enough, right? So we're going to see here that chloroform's hydrogen shows up at 7.27 ppm, no matter what instrument we use. And it's just going to be a nice little singlet because there's only one proton, doesn't see anything, there's no other protons messing with it or anything, so we just see one nice little peak at 7.27 ppm. So you might be asking, why is it important to use a more expensive instrument than if everything shows up at the same place? Well, we'll see that later. So we'll address that later on. But let's take a look at factors influencing the chemical shift. Typically, we're talking about heteroatoms nearby. And we're going to see, we can also talk about double or triple bonds and how they affect things. Otherwise, we're going to see some standard numbers here. So we're going to see typically, methane will show up at about 1.0 ppm. We're going to see that a CH2, or rather, so something like a methyl substituent, shows up at about 0.9 ppm. If you have a CH2, that usually shows up about 1.1, 1.2 ppm, somewhere around there. And just a CH by itself is about 1.7 ppm. So these are our kind of base values. All right, so depending on what you're looking for, methane, I mean, I don't even know why I put that because we're not going to be looking at the structure of methane, so go away. Methane is not relevant here. Depending on what type of hydrogen you have, by the way, these are called methyl hydrogens. These are methylene hydrogens, and this is a methine hydrogen. Those H's on those carbons. These are typical chemical shifts for plain old alkyl groups here. But we're going to see here that if we go ahead and mess with things, we're going to see what changes are going to come out. And you're going to see that sometimes you'll just see tables of all these values. These values are pretty reliable. Unlike in IR. IR is sometimes a little wonky, and it's kind of tough to say, well, this is off 50 wave numbers from where I thought it would be. Don't worry about that. With NMR, you can be pretty sure that things are going to show up where you expect them to. So we're going to see that the presence of oxygens, let's see here. So when oxygen is involved, we're going to have 3 different types. We're going to have I'm going to put the hydrogen we're looking at in a fancy color. If it's on the same carbon that is bound to an ether or an alcohol, we're going to add about 2.5 ppm to its value. So notice that because this is a methine hydrogen, it is a CH by itself. CH by itself is 1.7. So we would expect It's not a methylene because there's only one hydrogen on it. So methine hydrogens normally show up at 1.7. So we're expecting this to show up at about 4.2, if I can do my math correctly. Yeah, 4.2 ppm. This is where we would expect this thing to show up. If it were on a methylene group, so say now we have, equivalent hydrogens here. These would show up at 1.2, we'll say, plus 2.5, which will give us 3.7 ppm. So already we can see some difference in just the types of hydrogen that are on there. So an alcohol or an ether on the same carbon will give you an addition of 2.5 ppm. That's what we're looking at. If you have an oxygen that belongs to an ester, and in this case we're looking at these two that are next to an oxygen of an ester. That's why it's so important we learn these functional groups, by the way. This is going to make it a lot easier for us. Next to an ester will give you plus 3 for an ester. So these are our predictions, right? So we're going to see that we can combine all these things. So esters give us about 0.3. So starting with a methylene hydrogen, this will give us 4.2. So we would expect these to show up at 4.2. And you'll be like, well, how do we tell? These both show up 4.2. A methine hydrogen next to an alcohol or an ether shows up at 4.2. But here we have a methylene hydrogen that shows up. Don't worry. This is all part of the plan, right? So you're going to see, first off, in your chemical formula, do you even have 2 oxygens? An ester must have 2 oxygens. Do you have a carbonyl peak in your IR spectrum? These will be very important bits that we're going to put together to figure this out. So the 4.2 is pretty unique. There's only a few things that will give us 4.2. And so once we have our choices narrowed down, do we have an ether or an alcohol or an ester in this compound? IR can tell you that. IR will tell you have a blob for your alcohol. For an ether, you're not going to see anything. For an ester, you're going to see a double bond O at 1700. So all of this stuff is to be put together. So that's where the IR is useful. At a glance, you can say, I have an OH. That clearly tells me that this must be a CH next to, on the same as an OH. So all this information will be put together eventually. All right, so esters add 3.0. And if you have just a plain old carbonyl, that adds just 1. And again, here I'm using, here we can make it a methine group, why not? So that would be, carbonyl, no matter what type, any type of carbonyl, so ester, ketone, aldehyde, whatever, all of those will give you plus 1 ppm. So that ends up starting us at 1.7 because we have a CH. Plus 1 puts us at 2.7. And so that's where we would expect that hydrogen to show up. All right, so that's stuff next to oxygens. Let's talk about halogens. An iodine will add about 1.2. Bromine adds 1.7. A chlorine will add about 2.1. And a fluorine will add about 3.3. And so these are all just like things that would be on the same carbon. For example, this hydrogen is a methine hydrogen, only one hydrogen on this carbon. So that's 1.7 plus chlorine is 2.1, which gives us 3.8 ppm. So we'd expect this hydrogen to show up at 3.8. So this is the methine. This is the chlorine. Chlorine. Some people say chlorine. And you get 3.8. So halogens will add those. If you add multiple halogens, it's about the same thing as adding multiple. Just about. Let's take a look at the chloroform. This is a methine. It's roughly additive. If you do this, you get... I don't know, how do I add these things? Actually, it's a little bit different. It's a little bit less. So I normally you'll get, I don't know how to, 6.3. This puts us at 8.0. But we know it's really 7.27. So these are not quite additive. They're, each time you add one more, it's less and less effective. So kind of don't rely on this too much. It's a little bit less effective each time. So each one you add on. Because now you're de-shielding in different directions. You've got polarity and you've got all sorts of dipoles and all sorts of things happening. So because the electrons are being pulled away from that hydrogen or the carbon and hydrogen in different directions, that's why they're not all going to be 2.1. So we don't actually see that these are super additive, but they do. There is some additive thing. So obviously going from 3.8 to 7.2, we are obviously way more downfield. Right? We're way more de-shielded by having 3 chlorines on there. But it's not the same as just putting 3 on directly. So just be aware of that. So like you might expect it to be 8, but it's not really 8. It's actually a little bit lower. So just keep in mind for that sort of thing when you're adding these together. They're not exactly additive. They're somewhat additive. So like for example, if you had something like this, you might expect, well, we have a methine, we have a chlorine, which is 2.1, and we have an alcohol, which remember is 2.5. Remember, alcohols here are 2.5. We might expect this to show up at 6.3 ppm. Let's find out. I'm gonna just check real quick where this one will show up, or where it's predicted to show up, because it's not going to be exactly additive. Here's my handy dandy. All right, let's see. All right, let's do this. So we've got bond to OH, bond to chlorine, and then whatever, we don't care about the rest. All right. Okay, let's see where this one will show up, or where we'll predict it to show up. So we might predict 6.3. However, where this will show up is about 5.68 or so, using magic mathematics. So again, a little bit less. Not quite additive. We have a little bit less than we'd expect. So just be aware of that. All right, so that's where we would find that. All right, so that's halogens, that's oxygen, and generally that's kind of what we see here. We're going to see that we have some other bits. We're going to see that allylic ones, these typically show up around 2 parts per million. Alkynes, this shows up about 2.5. So do aromatics. Aromatic, or like benzyl group, rather. These show up also about 2.5. Vinylic ones, though, these show up between 4 and 6 parts per million. There's a wide range there. We'll look at that more. Let's see. Aromatic ones are usually about 7 to 8. Very specifically, though, aldehyde ones show up at about 10, maybe 9 to 10, we'll say. They're very distinctive, very easy to see. And carboxylic acid ones show up around 12. We'll see that alcohol ones themselves these show up all over the place. I would hazard to say these show up between 2 to 6 or so. And they're kind of blobs. They're unresolved peaks. Somewhere around there. If you just see a random peak where you're like, I don't know what that is, and it's kind of blobby, it's probably an OH or an NH2. Like, why does that one show up here? They're different. So normally we're looking at carbon or hydrogen bound to carbon. Right? I didn't even put names on these. This is aromatic, or benzyl rather. This is vinyl. These are aromatic. These are aldehyde. These are carboxylic acid. Those show up there. Alcohols, amines, who knows? Big old range for those. And we're going to look at some of those in a little bit. So I'm going to just put that out for now. I'm going to also give you access to many, 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 many problems. And there's not going to be homework for this, but these are going to be ways you're going to test yourself. So right now we're just getting pieces out here. So we have 2 of our 4 pieces. So you can't do anything yet, but we'll get there. Alrighty. So that'll be it for today. So we'll continue on next time. Alrighty.